everyone, welcome back again on the series of ordinary differential equations. Last time I discussed about some applications where the this series or where the differential equations are used, and also told virtually about some physical applications and physical problems, and including both weather forecasting and also some like stock market and diseases, and also discussed about rocketry and satellite problems. So in all cases the differential equations are used widely, and it the theory of differential equation not only tell simplifies our problem but also give some extra informations also, and it does not give only one solution but a set of solutions, or you can you will see in the course. So last time as I said that I will be discussing some history and from here it starts. So let us trace out the road on which the theory of differential equation has come to this modern highway. So it was first, it was initially it was enunciated by great Isaac Newton, and at the same time independently by Leibniz. So around something around can you can say 1660 70 by Newton and Leibniz. So Newton enunciated the infinitesimal calculus. At that time, Newton gave in his book Method of Fluxions. So in chapter 2 of Method of Fluxions, method of, of fluxions, he discussed about three differential equations that are dy by dx is equal to f of x. This means function of x only. And second one was dy by dx is equal to function of x and y. And the third one was dy by dx1 plus, or you can say x2 times in two independent variable. This is a partial differential equation. So I'll discuss about what are the ordinary differential equations, and means I'll discuss about classes of differential equations. We so Newton discussed about these three differential equations, that is equal to y, where y is dependent variable. I'll discuss about this also. So initially it was developed by, or the you can say the at the initial stage it comes from the Newton and Leibniz, and further it was you can say it was supported by many peoples like Bernoulli, and there was whole family of Bernoulli, and John Bernoulli, his son Daniel Bernoulli, and Jacob Bernoulli. So there were a lot many Bernoulli. He they they developed this theory for in different times and different stages, and give also applied to the physical problems just like fluid dynamics and wave motions and etc. So Joseph Bernoulli, Lagrange, Euler, Leonhard Euler, D'Alembert, and you Lagrange, Maxwell, and D'Alembert give a wave equation that is known as, you might have heard about that in your 11th standard, that is uh, if y is wave function and it is function position and time, let a wave propagate in one dimension with time. So according to D'Alembert in 1746, so the equation was, for a wave propagating in one dimension, d2y by dx2 is equal to d2y by dt2 and 1 upon v square, where v is nothing but velocity or speed of the wave, or the speed at which wave is propagating in this direction. So you can, how can you remember this? Just you can use the dimensional analysis. In this, in this side, the dimension is inverse of what is inverse of position. If I say there is function sine kx, okay, what is the dimension of this? This is dimensionless quantity, because if I put some dimension to this, and we know according to Taylor expansion, I can express it uh, in form of polynomials. So it will be 1 plus x cube upon factorial 3, 1 minus x cube plus x to the power 5 upon factorial 5. So this, if it is position, x is the dimension of, or x is length, then its dimension will be meter. So these, the dimension of x cube and x to the power 5 will be different, so we cannot add these. So the dimension of this and the quantity that is in arbitrary constant or any constant will be such that the dimension of this and this will make this quantity dimensionless. Just you have seen that we write sine omega t. So the dimension of t is time and dimension of this is time inverse. It is because to make this quantity dimensionless. So if y is function of x and t, so it should be dimensionless, and this should be dimensionless. So dimension of this d2y by dx2 will be, if it is position, so it will be l minus 2, and here this will be t minus 2, and this is the dimension of this is 1 upon velocity inverse, so this will be l minus 2 t2. So this should be dimensionally consistent. So one can remember this equation easily using the dimensional analysis. And if we move further, then in 1750, at that time, Joseph Louis Lagrange and Lagrange and Leonhard Euler solved one problem that is known as what is known as, you can say, what, a curve on which, if this is a curve, okay, and if we leave, there are, these are the point balls, and we leave these points or these balls simultaneously, and whatever their position is, they comes at this position in same time. This ball, this ball, this ball, this ball. Let this be 1, 2, 3, 4. So if we leave these all balls at the same time, then these balls will leave the surface or the curve, this curve, at the same time. Such curve is called a cycloid. So Lagrange and Euler made this such type of curves are called tautochrome, and this problem is called the tautochrome problem or isochrome curve. So they made the differential equation for this curve, and further this was solved in about 5 years later in 1755. The differential equation for such problem was developed in 1750, and this was solved by Lagrange, and this this solution lead to the Lagrangian method or the Lagrangian solution, and which laid the foundation of classical mechanics, or the one formalism of classical mechanics known as Lagrangian mechanics. So whole Lagrangian mechanics or the whole Lagrangian formalism of classical mechanics also comes from this differential equations. It is nothing but the theory of differential equations. And if we go further, then there are lot many people who comes, and in this turn in 1822, Fourier comes with in his book the analytic theory of heat, in which he gave a differential equation known as Fourier heat equation. So, and there are lot many people who developed the theory, but these were the few people who supported, or who their contribution is uh, something more, or you can say that their contribution is groundbreaking. Or so this was little bit about history, and about it started in 1671, and it is 2022. So you can think the history, or you can think about the theory itself is not very old, but at the stage on which it has been reached is really amazing, or it applies to every problem of a physical world, just like you have seen the Newton's equation. It applies to the microscopic domain, that is where we use the uh, Newton's laws, and further development by Albert Einstein in his relativity, and general and special relativity, and also in microscopic world, that is Schrodinger equation. What is the Schrodinger equation? Let us look something about history of the Schrodinger equation, how actually it was developed. So at that time in 1922 or 1923, uh, at that time the Louis de Broglie has given the concept of electron waves, or the particles which have size very less size, and which are moving like electrons, have also the wave associated with them. So once one of the scientists, uh, we can say Pauli, asked to Schrodinger for the de Broglie's wave hypothesis, and he said to Schrodinger to give a very uh, you can say give something about this theory, and you should develop this theory, this wave theory. Then next time Schrodinger come with and make some all development and insights, and make his own some observations in the theory, and put it to uh, uh, phrase to Pauli. Then Pauli said that, oh, it is not. You have seen the D'Alembert wave equation. If these electrons are the waves, so this should these must have some wave equation, or these things must be represented by an equation. Then Schrodinger took about 1 or 2 weeks, and he did really very hard and work for that, and Schrodinger come with equation. Whether this equation is not derivable from anything else, yet yet what are the expectations, or you can say the what are the comes, or the what are the outcomes of the solutions really well satisfied with the physical or the experimental observations. So what is the Schrodinger equation, and what actually we should see what actually Schrodinger did. Schrodinger thought that let y x t be a wave equation for the electron waves. So it would be sometimes something like a e to the power I omega t minus kx. So this is a wave equation because it satisfies the D'Alembert's wave equation, that is that I discussed here, this equation. So it represents a wave, and what he used, according to Einstein, energy of a particle, or a oscillator, or you can say a anything is conserved, conserved, no, not conserved, means it's quantized, is h times nu. So we can write this, and nu is the frequency of oscillations, and we can write 2 phi e is equal to h omega. Omega is equal to 2 phi nu. So E is equal to h by 2 phi times omega, and we write this quantity is h cross. Okay, so omega is equal to E by h cross, and similarly, according to Louis de Broglie, phi is equal to h by lambda. So from here we can write, what can I write, that 2 phi by lambda into h by 2 phi is equal to p. So from here, what is this? This is in a wave propagation, or in string or anything else, this k is same as 2 pi by lambda. So we can write this as k is equal to p by h cross. This will be h cross. So we replace these two things in this wave equation, and we differentiate this, and we know about a particle, the total energy of a particle is sum of its kinetic energy plus potential energy. Okay, so let kinetic energy of the particle, and we know the kinetic energy is half m times v square in non-relativistic case. So we can write this as p square by 2m. Okay, and this say that potential energy be v. Okay, so we can write this e psi, or ey, we have taken e function, wave function is y, so ey is equal to p square y x t upon 2m plus vy. And if we differentiate this equation by putting omega is equal to E by H cross and K is equal to P by H cross, then differentiate to find out E psi and or EY and P square Y, we get that this quantity is I by H cross del Y by del T, okay, is equal to minus H cross square by 2m del 2y xt upon del x2 plus vy of xt. In quantum mechanics, they take the wave function not as y but psi. So we can write on reducing this equation or manipulating, just that is h cross square by 2m del 2 psi by del x2 this side plus I by h cross del y by del t is equal to v psi. This equation is known as time dependent Schrodinger equation, and if we don't allow time is independent independent variable, then this equation reduces to h cross square by 2m del 2 psi by del x2 plus e minus v of psi is equal to 0. This is nothing but a differential equation. So whole quantum mechanics is nothing but solving this differential equation for the very variety of this potential energy function, and not only in one single dimension, but we apply or allow the position vector or not only in one dimension but in three dimension. So in case of three dimension, this becomes h cross square by 2m, and this becomes a partial differential equation del 2 psi by del x2 plus del 2 psi by del y2 plus del 2 psi by del z2 plus same all things. If we allow for we this in this time or in this case, this will be position, this will be function of x, psi will be function of x, y, z and t. In that case it is function of x and t only. So you have seen, and you will be comfortable, and you have a clear idea that uh, why one should study the differential equations. And we can also discuss about heat problem and something extra, but I'll stop here, and in next turn I would be discussing about types of or the classes of differential equations, and then the theory of the differential equations. It is enough to get an idea that in which or how wide the subject matter of the differential equation is. So hopefully you will enjoy, and you are enjoying. Take care.